Alright, welcome. This is the virtual edition of the Thursday Forum, What Mathematics Do Elementary Education Teachers Need to Know? I'm Brett Benish. I'm an assistant professor of mathematics at St. Ben St. John's. It's no longer spring 2012. I'm speaking to you from the future. It's now spring of 2014. So let's start with something that I think most mathematicians will be able to relate to. If you're not a mathematician, here's an insight into our lives. This is me at every single party I've ever been to. I go up and talk to someone approaches me and says, "Hey, what do you do, Brett?" "I'm a math professor." "Oh, I was never able to understand math." "That's okay. I never learned how to read." Now, this is the type of snark that I sometimes dream about in my darker moments, but I've never said it to anyone. I don't plan on saying it to anyone, because in part it's kind of cruel. But I think it because, as a mathematician, I think it's important to learn mathematics very naturally. I think it's not as important as reading, but it's up there. And there are a variety of reasons for that. For instance, there's just the annoying stuff, right? That if you're not all that familiar with mathematics, even basic arithmetic, which is just a very subset of mathematics, you might get duped into buying Guitar Hero 3 because you think you're going to save $12 when the reality is it's like $5. A very real problem is in the 2012 State of the Union address, President Obama said that we have twice as many STEM, science, technology, engineering, mathematics, jobs that are open that we are able to fill. That's 2 to 1. So we are not producing enough people who are competent in mathematics enough to do these jobs. And here's my favorite. This is from a textbook. And fortunately it's from a textbook because this would be horrible if it happened in real life. Okay, so basically in 2006, the median price of a home was $220,000. In 2001 is $150,000. So we're just going to use these two numbers, to predict how much houses are going to cost in 2010. And if you did that, if you wrote a linear equation, you would just assume that the housing prices go up and up and up. And if you were to do that, if you didn't understand mathematics and used a model like this, you might be tempted to put a whole bunch of those mortgages into mortgage-backed securities, and then you might be tempted to create credit default swaps based on them, and then you might be tempted to tranche those credit default swaps and put them together into to put the riskiest ones together and give them a AAA rating if you're a credit agency, because if you use this mathematics, you're going to assume that housing prices never go down by 2010. And since we know, I can't go on like this, right? We know what happened. Housing prices did go down, and it was because, I don't know, it probably wasn't because of mathematics this simple, but it's because people just made these assumptions and perhaps trusted mathematical models like this more than they should because they didn't understand the mathematics. A mathematician knows that you take all these predictions with a grain of salt, and there are a whole bunch of assumptions built in here. Someone who is not very comfortable with mathematics might think that mathematics is more magical than that, and might think that the mathematics causes house prices to go up. After all, you have an equation of a line here, and equations of lines can't be wrong. Okay, so the moral of this talk is that the more people do math, we won't have economic crises. I hope you take that away from this talk. All right, and so what we have, one of the big problems that I think we have in schools is an overemphasis on memorization and facts and calculation. As a mathematician, I really view mathematics more akin to an art. It's not just an art, but there's a lot more to it than just memorizing things and spitting stuff out and doing it. And you saw with the house prices one, you can see that maybe it's not just calculations, because you have to use common sense in that to interpret it and to know what assumptions you're making. And to figure out whether it should be a linear model or something else. So it's much more complex, and we need to teach that complexity, or else we're going to have a whole bunch of recessions. Okay, that's a little bit of hyperbole, but you understand what I mean. And besides, if you teach kids to memorize and to learn facts and to calculate, you're going to turn them into someone who has a skill set of a computer, except a computer or a robot is going to be able to do it much better than them. So I don't know that this is the only way you should be thinking about students, but one way to think about them is they're going to be economic players later on, and they need to have a place in society. And if the only mathematics they can do is what a computer can do, but they do it less accurately and more slowly, that means that they don't have math skills that will be useful to us as a society. We need to teach them reasoning skills and judgment skills used on the math. So what we really want to do in mathematics, in elementary school mathematics, really, because I'm talking about what teachers need to know, which is related to what elementary school teachers need to know, we need to understand what's going on. We need to break down what's going on with elementary school mathematics. So when we do that addition algorithm where we carry stuff, we need to figure out what's going on there. Why does that work? We need to get underneath the hood, so to speak, and look at the engine, rather than just put the key in and just drive it without even wondering if there's anything underneath the hood. So I'll give you some examples in this talk about what I mean by that. And here's the example I come back to a lot. Division of fractions. 2/5 divided by 3/4. A lot of us learned that you just invert this and multiply it. Just turn division to multiplication and do that. To me, that seems like black magic, at least at this point in time. And a popular saying among school teachers way back in the day, and I don't really want to date way back in the day because I'm scared that it might be more recent than I think, is ours is not to reason why, just invert and multiply. And that's absolutely the wrong thing to tell to a student, right? Because what you're doing is you're saying, hey, you don't need to be anything more than a computer. Don't reason why. Just do what we tell you. Just do what we program you to do. And that's a losing battle, and that is really doing our kids a disservice, our students a disservice, and selling them short. And it's not good for us either, because those kids are going to be taking care of us in the world. So I'm flipping this on its head. I'm saying, yeah, invert and multiply, but you better reason out why that works. That's the important part. That's where the mathematics lies. This is just calculation, and that is something that a $2 calculator can do. Something a $2 calculator can't do is understand why this makes sense in the world. So who can fix this? We have a problem with mathematics. Our kids aren't learning mathematics well enough. We have a society of people who are mathophobic, who tell me at dinner parties that they can't do math, they never understood it, and they are at best indifferent and sometimes even proud that they can't do math. So who can fix that problem? Here's what someone who can fix it would need. They need to be aware that there's a problem. You can't fix it if you're not aware of it. They need to know enough mathematics to know how to fix it. If all your view of mathematics is computation, you will not know that there's any problem, and you will not have the knowledge to fix it because you won't know how to get beyond the computation. They also have to have the opportunity. They have to be in a position where they can affect people's lives and make them more effective little mathematicians. So, who can fix this? The guy at the party? Almost certainly not. He probably has a job where, first of all, he's not aware of it. If he doesn't understand math, he doesn't have the knowledge to do it. And very few professions are really in a position to do anything about it. So he's off the hook. Our kids, our students, they're just there to learn. It's our responsibility to help them learn. So they are not responsible. It's not their responsibility. They should not be blamed. Much like the person at the party shouldn't be blamed, because he was once a student, and he got the education that was given to him. Teachers can play some part, but the reality is they're products of their education as well. They might not be aware there's a problem. They might not have the knowledge. They might. And there are some dedicated teachers who are working on this, and thank goodness for them. They definitely have the opportunity, but there's a lot of work to get the knowledge up to speed, especially if you have a very traditional education. And I'll show you the education that most teachers get very soon. So I don't know if you can rely on them, because the average teacher, I'm guessing, has a background in mathematics that is not what we want. That's not going to be helpful. Administrators, school administrators, they're kind of in the same boat. I mean, most of them aren't math teachers. They were never math teachers, and so they might not be aware. They might not have the knowledge. They probably don't have the knowledge because most people don't. And they might have the opportunity, although I've also been in some situations in K-12 education where top-down approach wasn't all that successful. So administrators, they're not going to be the solution. I'm not even going to comment on politicians, so let's just skip them over. That leaves professors. Math professors. Math professors know mathematics. They are aware that there's an issue because they go to parties and people talk to them like that. They have the knowledge to do that because they know what mathematics is, and they know how it's used, and they know how it should be used. And they have the opportunity, at least at many schools, where they teach teachers, and certainly we have the opportunity here. So, let's see what we do. Math 121 is our class for elementary education majors. So, here's what is in the course. It's primary for elementary education majors: addition, subtraction, multiplication, division, both on the integers and on rational numbers and fractions. And that is really the core of the course. And here's my axiom for any sort of a teacher education course. There's just too much stuff. You can't teach them all the stuff in 1 to 2 semesters. We have to, right? We have real-world constraints that says that we only have 1 to 2 semesters because they need to graduate eventually. But I can't teach them everything they need to know. So the approach, which I hope is successful, I don't have strong evidence for it yet, but I'm going to try to teach them, put them in a position where they can teach themselves everything else that they need to know. So, in other words, I'm going to teach them stuff about this, but I'm also trying to teach them how to think correctly about this, more so than just teach them a whole lot about addition, a whole lot about subtraction. I'm just trying to get them the right mindset so they can apply the mindset to whatever they need to teach. And the great barrier to this in most colleges is that textbooks, I find, are working against the college professor who's trying to improve the teacher's knowledge of mathematics. And so what I did in spring 2012 is I got a teaching and scholarship and teaching fellowship. I'm writing a textbook, and I have been for some time, with Aaron Weinberg, who's at Ithaca College. And we're trying to create a textbook that helps the professors get the students to where they need to be. And so why don't I like the current set of textbooks that are out there? There's a pedagogical problem in that the education department, which that's what future teachers are majoring in for the most part, are teaching one thing, and in most mathematics classes that the elementary education majors take, they're being contradicted in practice, if not in words. So in other words, the education department says, here's what good teaching looks like, and then they don't see that in mathematics. And part of the reason for that is that the textbooks are set up to really make it hard to follow the education department's advice. And here's the big issue. Here is a typical mathematics textbook. And what you can see here is that stuff is highlighted. I very naturally would be inclined to skim this and read that, skim that and read that. The textbook author is telling you, hey, this is the most important stuff. As a student, my time is valuable. It is completely rational for me to spend a lot less time on this and focus on that. A lot less time on this and focus on that. And the problem is that these are just the results. And I told you that we really need to get and look underneath the hood and see what's driving these results. Why are these true? But this textbook is laid out in such a way such that makes it really difficult to do. Instead, here's what we do in the first day of our class. This is our setup. Hey, we have a game. You take turns. You've got to play 10 cookies between you two people. Take turns. You can either take 1 or 2 cookies. The person who takes the last cookie loses the game. Your goal is to understand winning strategies for the last cookie. So I give them a game, give them a list of rules, and I set them free to go about it. So let's take a look. Here's what the whole textbook looks like, right? This is the first lesson, the first day. Here's page 1. Here's page 2. And that's really all there is to it. Notice how little text there is. There's not a lot of text, so there's not a lot for the student to really look at and just say, oh, this is what I need to memorize. In fact, all I've really done is given them rules on the previous page and a set of questions on this page. So So what we've done is we've basically offloaded all of the content into the instructor text. We understand that there's a lot of stuff that's actually pretty tricky in the Mathematics for Elementary Education majors courses. You might think it seems easy because it's arithmetic, but arithmetic is actually much more complex than people think. So what we've done is we've offloaded all the stuff there. So we tell them, okay, summary, justification, materials, timeline, solutions. Here's how you solve it. So before class, an instructor can read it and get to know it. We tell them what the potential difficulties and how to scaffold those difficulties. And so this is designed to encourage professors to get their elementary education majors to think through the mathematics on their own, which is a very good skill for a teacher to have, because that's what they're going to need to do for the most part. They need to teach something the next day. They need to learn it. They're not going to be able to go take a class on it in 24 hours. And here's the last page. So we've offloaded all the heavy lifting to the instructor text so that the instructor has the knowledge to help the students reason through it, but we didn't just give it to the students. And here's a second problem with the textbook, and I hope you'll indulge me with a little hypothetical here. Imagine high school French teachers. Now, high school French teachers in this hypothetical are being trained all wrong. And the reason why is because it's a little embarrassing that they get to go to college and get credit to learn French, because French is easy. French is easy. After all, like 2-year-olds can speak it. If you go to France, right? You can walk on the street and like little kids speak it. So it's not difficult. So there's no real point in getting college credit for such an easy thing. So here's what we're going to do. So we want our French teachers, they have to be able to teach French, obviously, but it's not worth our time to teach French to the college students. So what we're going to do is we're going to teach them Latin. Right? Latin's hard. Very few people speak Latin, so it's worthy of college credit. Moreover, French and Latin are related, right? French is a Romantic language. It comes from Latin. So if you understand Latin, you'll be able to pick up the French really easily. So we should teach French teachers. We're not going to teach them French anymore. They may have learned a little bit of French in elementary school or middle school. That'll be enough to go by. But once they've learned Latin, we'll assume that they know enough French to teach French to high schoolers. Obviously, this is meant to be a little absurd. But that is actually what we're doing with our elementary education teachers with mathematics. Right? So let's see this in action. Xander starts with 3 apples, and Spike gives him 2 more apples. How many apples does Xander have now? This is an addition problem. Right? The way you normally solve this is 3 plus 2 equals 5. So one thing that I don't think we do enough of is we don't actually tell students what addition is. We just kind of give them a whole bunch of addition problems and say, go figure out what addition is on your own. So if you want, I encourage you to pause this and try to write down what you think addition is right now. And I'm about to give you the standard textbook answer. Textbooks anyway for college courses for future elementary education majors. So it would be really nice to tell students what addition is so that when they read this, right, a lot of students have difficulties with word problems, they can have something to say, okay, is this an addition problem? Well, I know what addition is, so I'm going to test it against that. Is this a subtraction problem? I know what a subtraction is, so I'm going to see if that's the situation. So here's what one of the leading textbooks says is addition. Let A and B be 2 disjoint finite sets. If n of A equals A and n of B equals B, then A plus B equals n A, some cup thing that you actually pronounce union, B. E pluribus unum, etc. Right? I mean, what we've done is we've said, hey, addition is too easy, so we're not going to teach these college students addition. So we're going to teach them some set theory. We'll teach them in terms of set theory. And this is not relevant to teaching elementary school kids mathematics. You are not going to teach kids about 2 disjoint finite sets. You're not going to say one finite set is 3 apples and 2 finite sets, or a second finite set is 2 apples, and they're disjoint because his apples are different from Spike's apples. You're not going to do that. So this is not relevant directly anyway to teaching elementary school mathematics. It's relevant in the same way that Latin is relevant to teaching high school French. But you might think I'm cherry picking. And perhaps I am. So let's look at a different textbook's definition of addition. Let A and B be two whole numbers if disjoint sets. Okay. Yep, so this is the second leading. And these are roughly the two most popular books. I don't have the numbers in front of me. I'm guessing well over half of the future elementary education majors in this country are seeing one of these two definitions of addition. Ad absurdum. Okay, what could it look like? Well, here's what we do in the textbook. We tell students to create word problems for which 6 plus 11 is a solution. So I'm going to leverage my students' knowledge of what addition is. They know it when they see it. But from there, we're going to, again, get underneath the hood and try to extract what's in their mind. They have some sort of an intuitive sense of what addition is, but very few of them have ever even tried to put into words. Probably because very few of them have been asked to put into words, and probably very few of them have seen anyone put what addition is into words. So they come up with a bunch of questions. And these are actual questions from my Math 121 class. Right? Zach has 6 apples, Brett has 11, they share. Cindy has 6 kittens and finds 11 more. How many does she have now? 6 bags of chips, then 11 bags of chips. How many chips? These are all addition problems. 6 plus 11, 6 plus 11, 6 plus 11. Then we have the students go through and try to figure out, okay, this is about apples, that's about kittens, that's about chips. You're telling me that these 3 have something in common. What is it? Here's what they come up with. In all 3 of these, you combine 2 groups of known quantities, 6 and 11, and count the number of things in the resulting group. So you combine the 6, combine the 11, and you have a pile of stuff. Count how much stuff is in that pile. You happen to get 17. But this is the addition process. This is something that is very relevant to teaching kindergartners, first graders. A kindergartner or first grader can understand this definition. They will not understand finite disjoint sets. Yet it achieves the same thing. It's just less formal mathematically, but it's more appropriate for the age level they're going to teach. It is French, not Latin. Right? So combine 2 groups, 3 apples, 2 apples, then count how many apples does he have now, count them in the resulting group. Alright, let's go back to this one. Inverting and multiplying. Let's see how the leading textbooks deal with this. So if you want to divide 2 fractions, like I just showed you on the previous slide, this textbook, one of the leading textbooks, says, there are 3 ways of doing it. This is the ironic part of the lecture, because you can focus on these 3 methods, and this is invert and multiply. There are a couple other methods. If you have the same denominator, you can just divide numerators. You can divide numerators and divide denominators. All 3 of these work. Very few of them are taught. So it's good that that college students are learning these 3. It's very good. I'm happy that they're introducing them. The ironic part is off to the side here, an NCTM standard, the National Council of Teachers of Mathematics, I believe is counted. So these are standards that they say should apply for high school students. All students should develop and analyze algorithms. What algorithms are the students developing here? These are the only 3 reasonable algorithms I know for dividing fractions that I'm aware of that can be written down like this. So you've just taken away every chance that the student has to develop a reasonable algorithm. So this is the problem I have, is that the textbooks are doing too much for the kids, the students. Sorry, we're talking about college age students at this point. So what else do we find? Here's another example. Division. We'll give you this as an example. We're going to divide these and set it equal to E over F. And then you can multiply both sides. Essentially, this is algebra, right? We have variable. Okay, so how is this relevant to teaching 4th or 5th graders to divide fractions? They haven't had algebra yet. They probably haven't seen any variables. So we're going to teach them how to divide fractions in college, but we're not going to teach them in a way that's going to be useful for them to teach their students. So, very similar here. We're at least avoiding variables. On the other hand, in other ways this is nicer. On the other hand, we're doing some trickery here. we're multiplying top and bottom, which is good. I wish they would explain why why you're allowed to do this and why this makes sense in terms of fractions. And then you use the algorithm, right? Divide numerators, divide denominators. It's not the standard algorithm, but it's an algorithm. So essentially here they're just teaching you how to solve an algorithm, and they're just making it kind of doing it in an easy way. And they're showing how this algorithm is equivalent to that algorithm, the invert and multiply. So, and that's good. It's good to draw relationships between, find the invert and multiply algorithm from this algorithm. But also, the students aren't developing it. The students aren't analyzing it. It's being done for them. They're showing you how to do this. Here's another one with algebra. They're saying, you want to divide fractions? Set it equal to x. Your students won't know what x is. Your students might not be familiar with algebra. And then also, don't worry about division. Let's just push symbols around, and then we'll turn it into a multiplication problem, then we'll use reciprocals, etc., etc. So this is useful. This is incredibly useful mathematics to know, although I don't know if it's age appropriate for someone first learning to divide fractions, which our students aren't, but the message that they're getting, maybe, this is how you teach fractions. This is a good way to confuse a fifth grader. And finally, there's this, which is a way of dividing fractions that is completely devoid of meaning. And again, it's useful as a mathematician to sometimes trust the algorithms and do this. That is a useful thing, but we rely on it too much in school. It's much more useful to explain kind of what's going on here. So this is just a bunch of symbols that you move around, and it happens to come up with this, and then it's easy to get lost and not understand where this came up. Here's our alternative. We're just going to tell them what division is. Once again, there's no harm in telling them what division is. In fact, it makes life a lot easier for them. When they see a word problem, they can say, is this a division problem? Well, I know the definition. They have to memorize the definition or get to know it somehow. But they know the definition. So, by the way, there are two types of division, which is also something that needs to be taught. There's par division, so I'm just going to talk about that. I'm not going to talk about the other type. I have some amount of stuff. I have 6 oranges, and I want to share an equal amount with each of 3 groups. How many oranges does each of those groups get? And it's better, instead of saying each of those groups, how many oranges ends up in one of those groups. So again, this is an age-appropriate definition. An elementary school student could understand this. It might not be written the best, but this is what typically is typical of what our students come up with, and our college students can refine it with their elementary school students to have something that makes sense to them. But this is something my class came up with. And here's how we explain it. Why do you invert and multiply? We start with some amount of stuff, 2/3. And we represent it like this. This entire rectangle is 1. We cut into 3 pieces because that's what the denominator says to do. Cut into 3 pieces, and you take 2 of them. That's what the numerator says. Divide by 5/7. What does 5/7 mean? Take a whole thing, slice it up in 7 pieces. That's the denominator. And I will take 5 of them. So I shade 5 of them. And you actually don't need to draw this, and it might be even confusing because this rectangle should be different from that rectangle, because this represents the amount of stuff that you have, like oranges, and this represents groups. So, right, if I have 2/3 of a cup of flour go into 5/7 of a recipe, how much flour goes in one recipe? Well, the way to think about this is 2/3 goes in this much stuff, and I have 1, 2, 3, 4, 5 shaded things. So how much goes in one of these shaded bars? Well, that's just 2/3 times 5. But I need to figure out how much goes in one of these groups. And there are 7 of these little bars that make up a whole group. So then I multiply by 7. And then it's just some fractional multiplication, which we talked about prior to this, that just says, hey, this going from there to there, there's a lot of meaning here. Just take the amount of stuff you have, split it up equally among these 5, so each one gets 2/3 times 1/5, and then multiply by 7 to figure out how much would go in the entire thing. This has a lot of meaning, and then this is just kind of a mathematical trick that helps us remember it more by combining the 1/5 and the 7. This, in our college students do this, and this would be reasonable for someone in later elementary school to come up with on their own. Right? There's no algebra here. It's just understanding what division is. It's equal sharing. If you want to figure out how much goes in one of the groups, and you know 2/3 goes in 5/7, you can figure out how much would go in this entire thing by just splitting it up, as I said. So here we go, back to this. So we know that the textbooks aren't even asking the students to develop their algorithms. Well, maybe they have them analyze algorithms. Well, I'm not showing you the entire textbook, but this is a list of problems. This was taken roughly at random. You can see that it's divide, calculate, 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 calculate mentally, which is not bad, by the way. I think it's good to calculate mentally because it gets develops some flexibility. But nothing in here is talking about why does this even work? Why do these algorithms work? Let's analyze it. There's none of that. None of that on these problems or the other page either. So instead, here's what we do. We say, hey, you will be grading student work at some point. You will see students do stuff like that. I promise you. Here's what Alex did. Try to grade it. Try to figure out whether it's valid. Students will do stuff that will surprise you. Sometimes it's valid, sometimes it's not. Your job will be to decide whether it's valid, which means you need to get underneath the hood of this thing. Here's another one. Sasha does this. You need to get under the hood of this one and try to understand if it's mathematically valid. And this one, by the way, does work. It's completely mathematically fine. This one is mathematically flawed. In fact, even the answer's wrong. So we have the students actually analyze stuff, and we present it as student work, which the students like, because they can realize that, oh, it's important for me to do this because I'm going to need to grade as a teacher. Compare that to this. How much analyzing is done here? Again, this is just kind of pushing symbols around, which doesn't lead to much understanding. This is just kind of the magic of algebra happening here. Not even the magic of algebra, is pushing symbols around. Again, a useful mathematical skill, but we really over-rely on it in school. And the issue here is really almost we need to do no harm more than anything else. So students have come through K-12, and they may, most of them I think, are seeing a lot of just calculate and memorize and facts. And at the very least, we should do no harm and not reinforce that issue. Because we are PhD mathematicians. We are mathematicians. We are telling them, giving them an idea of what mathematics is. If a mathematician tells you that mathematics is memorization, you are probably more inclined to believe it. If a mathematician tells you that you're supposed to understand and analyze and develop, they're going to be more inclined to believe that. There's still a lot of inertia from 13 years of schooling, perhaps, but you might be more inclined to start changing your mind and start believing that mathematics might be a little different. So here we go. This sort of textbook encourages looking up facts and not necessarily understanding what they are. You just kind of understand what's in the boxes, and then you're good. Versus here, I don't give you much to go on. You need to figure it out on your own. The teacher's there to support you, and we have supported the teachers with a textbook, but you're going to have to think through and get used to reasoning through things. This definition of addition, or that one. Latin, French. Which is going to be more useful to a future teacher? This sort of reasoning and analyzing, or this? Right? I mean, I'm in favor of the stuff that I've been doing, but which do you think would be more useful for a student who's going to be a teacher, an elementary school teacher, to know? So here are some photo credits, some picture credits, more picture credits. You can pause if you're really interested, and I'll take questions, except this is a screencast, so I'll just say thank you. Again, my name is Brett Benish, at the College of St. Benedict, St. John's University. Google me, email me with questions if you have them. Thank you very much. I enjoyed this. I need to get out of here. There we go. Slightly embarrassing, but we're done.